How can we determine the order of a reaction and the units of K from our rate law equations? Let's find out. Rate laws are the way the rate or speed of a reaction depends on the concentration of the reactants. For example, consider some reaction with reactants A and B. Our rate law would be something like rate equals K times the concentration of A to the power of X times the concentration of B to the power of Y. Now, note it's X and Y, not little a and little b like we have in our reaction. That's because they don't depend on the reaction, and we have to find out what they are experimentally. What X and Y are, though, is known as our order of reaction. So in this case, our order of the reaction would be X with respect to A, and our order with respect to B would be Y. If we add them together, X plus Y would be our overall order of reaction. For example, if we knew what they were and we had a rate law where K equals concentration of A times the concentration of B squared, that reaction is first order with respect to A, because there's an unwritten 1 on top of the A, and second order with respect to B. And then 1 plus 2 is third order overall. Or, if we had something like rate equals K times the concentration of A squared, that reaction is second order with respect to A, because the exponent is 2, but 0 order with respect to B. Because B isn't written, we know its exponent must be 0, since anything to the 0 power is 1, which we don't write in our equation. Okay, but how do we determine the orders of our reaction from experiments? Well, let's say we ran the experiments in this table where we measure the rate of reaction changing while we also change the concentration of our reactants, A and B. And as we look at this table, we'll notice that we've held either the concentration of A or B constant in some of these trials, meaning we've used the same concentration twice for each of them. That's because if we want to know the effect of A's concentration on the reaction rate, we want to hold B steady so that we can ignore it. Let's see why this works and determine the order of reaction with respect to A. Looking at our table, we see in trials 2 and 3 we held the concentration of B constant, so let's work with those. To compare the rates, we're going to divide them, and when we do that, we'll see that the rate law of trial 2 divided by the rate law of trial 3 already lets us get rid of K. Because it's a constant, it doesn't change, and anything divided by itself is just 1. Then if we plug in our rates and concentrations for each trial, we see that because the concentration of B didn't change, we again have something on both sides of the fraction that we can cancel out. And now we're only left with X, and we can solve for it. 2 to the X equals 4. That means X must be 2 because 2 squared is 4. So by holding B constant, we could ignore its effects on rate, and we could cancel it out in our equation and solve for the order with respect to A. Now we can do the same thing to find the order of B using trials 1 and 3 where A is held constant. And since we know that the rate constant and the concentrations of A are going to cancel out, we can skip right to comparing how the concentration of B changes relative to the rate. This time, as concentration of B doubles, the rate also doubles, and so we get 2 equals 2 to the Y, which means Y must be 1. So putting that together, our rate law must be second order with respect to A, and first order with respect to B, or rate equals K times the concentration of A squared times the concentration of B. And now that we know our exponents, if we want to find K, we can just pick a trial and plug all the values in. K will be the only unknown left, and we can solve for it. So, for example, picking trial 1 and plugging in our concentrations of 0.1 for A and 0.4 for B, and our rate of 2, solving that all out gives us K equals 500. But 500 what? Let's actually take a look at the units of K. So the units of K are going to depend on the overall order of the reaction. But let's simplify a little and assume that we only have one reactant, A, so that our overall order of the reaction and our order with respect to A are going to be the same. But these units will account for the overall order of the reaction. Looking at our rate law, we know that rate will always have units of concentration per time, or most commonly molarity per second. Concentration will always be molarity, but for every different order with respect to A, we're going to have different units of K. If we solve for K, we see the concentration and order of reaction ends up on the bottom with seconds. So if we plug that into our table, we can solve each of these reaction orders for the units of K. So for 0 order, molarity over molarity to the 0 times seconds, molarity to the 0 cancels out, and we just get molarity per second. For first order, molarity over molarity to the first power times seconds, molarities this time cancels out, and we just get 1 over seconds. For second order, my molarity on the bottom is squared, so I get molarity over molarity squared. One of those cancels out, and I get 1 over molarity seconds. For third order, Again, I have molarity cubed on the bottom, and one of those is going to cancel out from the molarity on the top, and I'll get 1 over molarity squared per seconds. Or if we don't want to rearrange the equation and solve for these units every time, we can just remember this formula. The units of K is going to be equal to 1 over molarity to the power of the order of the reaction minus 1 times seconds. Now, if we want to look at concentration over time for each order, we can do some calculus and get our integrated rate laws. We're going to ignore third order reactions because they're rare. With these integrated rate laws, they're going to allow us to plot the concentration versus time for each order because we see that they're all in the form of y equals mx plus b, which is our slope-intercept form for our line. And since each order has a different equation for its line, that means that if we measure our concentration over time and plot it, then depending on what we use for our y-axis and which one of those gives us a line, that will tell us what our order of reaction is. So, for example, the zero order reaction, that graph will be a line if we plot concentration versus time. Or for a first order reaction, the data will form a line if we plot natural log of concentration versus time. And for a second order reaction, it should be 1 over concentration versus time would give us a line. These graphs also give us another way to find the units of K. Since K is the slope in these equations, we can take our y-axis divided by our x-axis, and that will give us our units of K. For first order, concentration over time gives us molarity per second. For second order, we have to remember that natural log has no units, so natural log of concentration over time is really just 1 over time. And the way you can remember that is the natural log likes to go au natural. Or the L kind of looks like a 1, so if you just erase everything else next to it, you get 1 over seconds. And for the second order reaction, we have 1 over concentration over seconds. And so remember, when we have a fraction on top of a fraction, we can move the denominator of the top fraction to the bottom of the whole fraction. That puts concentration on the bottom with seconds to give us 1 over molarity times seconds. And that's it. That's how we find our orders of reaction and our units of K.